Hi, I'm Rob Heinemann. I'm a professor of statistics in the Monash Business School. Most of my research concerns time series analysis, especially forecasting and analysing large collections of time series. I'm particularly interested in uncertainty and understanding, describing and evaluating the uncertainty about the future. When I tell people I do forecasting, they almost always assume I do one of two things, either that I forecast the weather or that I forecast the stock market, but I do neither of those things. The best way to understand what I do is to provide some examples of how my work is used. An early project I did was forecasting the total cost of the pharmaceutical benefit scheme for budget purposes for the federal government. When Australians go to the pharmacy to buy pharmaceutical products, they sometimes get subsidised by the government, and so the government needs to forecast the number of sales of all those different types of products in order to plan for their future expenditure. And I helped develop the tools that they now use to do that. I've also worked for each of the state governments to help with forecasting peak electricity demand, the maximum demand that's going to be needed in several years' time. And they use that to inform their planning around generation capacity. Pretty well every retail company in the world now uses forecasting, and many of them use my algorithms to help forecast retail sales, and that helps them determine stock ordering policies. An interesting project I've been involved with in the last couple of years is forecasting tourist numbers in Australia, particularly the tourism recovery post-COVID. It's obviously a challenging problem because the data from the past is not going to be very similar to the data in the future. I've also been working on forecasting COVID-19 cases to help each of the state governments and the federal government form appropriate policy responses. And since the start of March 2020, we have provided weekly forecasts that are used to determine what sort of lockdowns or freedoms need to be introduced in order to help control the spread of COVID. The beauty of mathematics is that it's very general, and that the same methods that I developed for the PBS are now used by Coles in their retail forecasting. The same methods I developed for forecasting peak electricity demand are now being used for forecasting groundwater levels in New South Wales. When I began my career, forecasting was considered something of a backwater, and I was strongly advised not to work in this space. It was hard to get published, and many researchers considered it a somewhat trivial application of limited interest. But while I was doing my PhD, I was also working as a statistical consultant, and I could see there were a lot of unsolved problems, and people in business and industry were using substandard methods that could easily be improved. So not being one to follow the crowd, I decided it would actually make a good area to focus my research attention. And I think I've been proved correct over time. As more and more data has been collected, the need to have automated forecasting methods has grown. And so I've done quite a bit of work on developing automated approaches to forecasting, which are now very widely used in business and industry. A spin-off from my research papers has been the software I write in the form of R packages. Each time I develop a new forecasting method or a tool, I provide an open source implementation that can easily be used. That's made a tremendous difference to both the number of citations of my work and the impact of my work. I've produced about 50 R packages, and they're now downloaded by several million users every year. Some of those packages are shown there. Forecasting is largely a problem of trying to quantify your uncertainty. Of course, no one knows what the future holds, but we can estimate what are the most likely futures and what are very unlikely events. It's a matter of building probability distributions that describe the uncertainty of future events. Let me give you an example. Suppose we were interested in forecasting the number of short-term visitors to Australia. Here we have some monthly data since the start of 2000 to the end of 2017, and we're trying to forecast the next few years. You can see there's some quite significant seasonality because people come to Australia more at some times of the year than others. There's a little bit of trend, particularly in the last decade, and there's also a fair bit of sort of irregularity and uncertainty in the data. If we fit a model to that series, we can use, for example, the ETS framework, which is one of the frameworks that I've helped develop. And then fitting a model to the training data, we then simulate the future from that model. So we get a possible sample path of what the future might look like in the coloured series. But we can do that again with the same model. We can run forward another time with a different set of random inputs, and we get a different possible future. And as we do this, we can build up an understanding of what the plausible futures might look like and what the unlikely events are. So we slowly build up an idea of what all of the different possible futures might be. And then we can summarize those using probabilities. So for example, we can find the mean future, which is the blue line. We can find the 50% most likely futures, which is the darker shaded region. If we zoom in, you'll see it more clearly. So the darker shaded region contains 50% of the possible futures, the light shaded region, 90% of the possible futures, and then some futures are outside the 90% region. So what we've done there is to try to look at the probability distributions of where the future might lie. Often the users of forecasts are less interested in the mean, the blue line, as they are in the extreme tails. For example, the various health departments around Australia are most interested in the upper tail of our COVID-19 forecast. What is the 99th percentile of possible outcomes, the 1 in 100 event? And so most of my work is about trying to understand and quantify and evaluate this future uncertainty. Of course, these particular forecasts were not very good after the first couple of years. So you can see that the black line, which is the true values that occurred during 2018 onwards, they tracked our forecasts extremely well up until around March 2020. And this is an example where the assumptions that we were making were not held throughout the forecast period, which leads me to say something about, well, what makes something easier to forecast? And I've come up with 4 factors, four components that you need to produce good forecasts. First, you need to have a good understanding of the factors that contribute to the thing you're trying to forecast and that you can measure those factors. Secondly, you need a lot of data available. Third, you want the future to be somehow similar to the past in a way that you can build into the model. And fourthly, you don't want your forecasts affecting the thing you're trying to forecast. So in these short-term visitor forecasts, 3 of those conditions are satisfied, but the future is not the same as the past, particularly since March 2020. So that was one component that was not satisfied and our forecasts are therefore not very good. If I was forecasting the stock price, the 4th one is a problem. The forecast can affect the thing you're trying to forecast. A good forecast of the stock price, if it's done by a well-known person and publicized, then the prices can change in response to that. And that's one of the things that makes the stock market a difficult thing to forecast. Forecasting has a very long history. Babylonian forecasters used the distribution of maggots in a rotting sheep's liver to predict the future, a little bit like reading tea leaves in a cup. And they trained budding forecasters at the Babylonian tertiary institutions, except they probably weren't tertiary, the Babylonian universities, by giving them clay models to show how to do that. So this is a clay model of a sheep's liver from the British Museum. And these squares, the sheep's liver is divided into these squares, and where the maggots were, which square the maggots were, was supposed to mean something about how the future would unfold. The fact that we even find these clay models shows how widespread forecasting training was. So this was about 600 BC, and around the same time, people wanting forecasts would also journey to Delphi in Greece to consult the oracle at the Temple of Apollo. And she would provide her predictions while intoxicated by ethylene vapors. So fortunately, we no longer have to get stoned on hallucination and get hallucinations through these vapors when we do our forecasting. Forecasters have had a bad name over time. The Emperor Constantius issued a decree in AD 357 forbidding anyone to consult a soothsayer, a mathematician, or a forecaster, saying, "May curiosity to foretell the future be silenced forever." A similar ban on forecasting occurred in England in 1736 when it became an offence to defraud by charging money for predictions. And the punishment, 3 months imprisonment with hard labour. Fortunately, forecasting is now legal and hopefully based on a more solid statistical foundation. A measure of the way forecasting has changed even recently is the impact factor of the main journal in the field, the International Journal of Forecasting. I was its editor-in-chief for 14 years up until the end of 2018. And during that time, the impact factor increased from 0.4 to 3.4. So forecasting has come a long way, both over the last 2,500 years, but also over the last 20 years. And I'm delighted to see forecasting now receiving greater recognition as an important scientific and research problem, and that I've been able to play a part in making that happen. Let me finish by just giving some ways people can contact me, and there's a URL if you would like to get a copy of these slides. Thank you.